Drop an apple from a tree, and its path to the ground is smooth and predictable. But zoom in close enough to the atomic level, and that predictability vanishes into a buzzing, chaotic cloud of probabilities. This mismatch is the most stubborn headache in modern physics. The smooth, exact rules of Einstein's general relativity, nature proposes an alternative. What if gravity is the exception? What if spacetime is the sole fundamental force that remains entirely classical, never breaking down into quantum pixels?
Physicists previously rejected the idea of a hybrid universe because mixing a definite classical field with a hazy quantum particle tends to break the basic laws of probability, producing mathematical impossibilities like negative likelihoods. However, researchers have now proven that a classical quantum hybrid is mathematically viable. But to make the equations work, the universe has to make a physical compromise, one that we can test right now. The rule governing this hybrid theory is that classical spacetime cannot remain perfectly smooth while it interacts with quantum matter. Spacetime diffusion requires the fabric of spacetime to randomly fluctuate to keep quantum systems fuzzy. The more spacetime diffuses, the longer a particle survives in superposition. If spacetime freezes still, the classical field forces the superposition to instantly collapse, causing gravitationally induced decoherence. Therefore, if gravity is truly a classical force, this spacetime jitter has to physically exist, and that gives experimental physicists a specific target to hunt for. To test if this jitter is real, researchers aren't looking out into the cosmos. They are using two extreme tabletop experiments to trap this theoretical fluctuation from both sides. The first experiment acts as the floor. By firing large, complex fullerene molecules through an interferometer, scientists can measure how long these structures survive in a state of superposition. Because they survive for a measurable fraction of a second, the hybrid theory dictates that a minimum amount of spacetime jitter must exist to keep them from collapsing. The second experiment acts as the ceiling. This Cavendish-style torsion balance is designed to measure the exact mass of physical objects with extreme sensitivity. If the fabric of reality is jittering violently, that background noise would blur our ability to weigh an object accurately. Our highly precise measurements of standard masses, like these pristine kilogram weights, prove that the background jitter cannot be extreme. The fact that we can reliably measure mass sets a hard maximum limit on how much spacetime could possibly be fluctuating. Spacetime diffusion is now caught in a physical vice. It has to be strong enough to keep molecules fuzzy in an interferometer, but weak enough to let us precisely weigh a kilogram on a scale. This chart shows the parameter space, the narrowing gap between the interferometer floor and Cavendish ceiling where classical gravity can exist. Current data has squeezed this gap so tightly that several models of classical gravity are crushed out of existence. As measurement technology improves, next-generation mass standards and molecular interferometers are going to push those boundaries even closer together. If that parameter space closes completely and we still haven't detected any gravitational jitter, classical gravity is mathematically dead. Spacetime would have to be quantum. We used to assume that proving the quantum nature of gravity would require building a particle collider the size of a galaxy to smash atoms together at impossible speeds. Instead, the true nature of spacetime is being tested right now, trapped between two highly precise devices sitting on a laboratory table.